for 2019 level 3 waves paper. So we're going to have a look at question 1, homemade guitars. Sarah builds a simple guitar using a hollow wooden box as a resonator and 3 strings on a wooden fretboard. She fixes the strings between 2 bridges that are separated by 0.736 meters. Alright, so this question, okay, we're going to see, I can't see the picture because it's copyrighted, but in this case, the length of the string is equal to 0.736 meters, so this is actually the length, that's the length of the string. So question A, in the space below, sketch the 4th harmonic that is formed when the string is plucked. So for the string, we know that on each of the ends, it acts as a fixed end. At the fixed end, when the waves are approaching, it's going to undergo a 180-degree phase change when it undergoes a reflection. So when it undergoes a 180 degrees phase change, it's going to interfere destructively with incoming waves, and it's going to create a node point. That's a point of minimal disturbance, and that's going to happen for the same of both sides. Okay, so in this case, we're going to have a point of minimal disturbance and a point of minimal disturbance on both sides. The 4th harmonic basically says that there's going to be 4 points of antinodes. There's going to be 4 antinodal points between the 2 nodes at the end. Okay, so in the actual exam, you're going to be measuring out the length of the string and then equally spacing the 4 antinodes. But in this case, I'm on my digital device. It's going to be very hard for me to do this. I'm going to try my best to draw out the harmonic, but it might not look very pretty, so just bear that in mind. So in the actual exam, you're probably going to be measuring out the exact length and splitting it into 4 equal parts. Okay, so antinode 1, antinode 2, so boom, boom, so 3, antinode 4. Okay, so probably won't look great, but right, so that's what our diagram should look. It doesn't look very perfect, I know. It's probably get marked down if you draw something like this in the actual exam. But because I'm on my iPad, it's going to be very hard for me to draw a very nice diagram, unfortunately. But it should look something like this. Okay, so we have our nodal points here and antinodes here. And that's just an achieve level question, so you can get achieve overall for this question. Question B, the speed of the wave through the string is 289 meters per second. Calculate the wavelength and frequency of this harmonic. So we know that for the 4th harmonic, we have 2 complete wavelengths that fit into the length of the string. Therefore, wavelength is equal to length over 2. A good trick, we know that when the ends are open on both sides or closed on both sides, we can say lambda equals to 2L over n, when n is the nth harmonic. So in this case, lambda equals to 2L over 4, which equals to L over 2. Okay, so just a neat trick to keep in mind. So lambda in this case equals to length, which is, 0.736 over 2, and 0.36 over 2, that will give us a wavelength of 0.368 meters. And now we can say that V equals to F lambda, and V equals to 289 meters per second, and therefore 289 equals to 0.368 F. F equals to 785 hertz, and that's in 3SF. And that's our final answer for this question. Okay, so for this question, I believe it was a merit level question. Let me double check, sorry. Yes, a merit level question for correct frequency. Correct wavelength will get you an achieved. The 3 strings on the box guitar produces different fundamental frequencies when played, even though the strings are the same length and made out of the same material. Because the strings are made out of the same length and the same material, the mass per unit length will stay the same. But that's kind of assuming that the mass is evenly not necessarily evenly distributed, but let's just say that the mass of the material through each string is consistent, so it's the same, and the length is the same. Therefore, the mass per unit length stays the same. Therefore, we can alter the tension of the string in order to change the speed of the wave in the string. For these questions, it's important to note that some people say that the speed of the wave in air will change. That's incorrect, because the speed of the wave is purely dependent on the property of the medium. Because the medium of air isn't really changing, Therefore, it's incorrect to say that the speed of the wave in air is changing. The speed of the wave on the string is changing because we're altering the medium of the string, because we're altering the tension of the string. Therefore, the speed of the wave on the string will change. Because it's changing, a different set of resonant frequencies will be used to produce standing waves, and therefore the fundamental frequency will change, and therefore it will be at different frequencies. Okay. So for this question, we can say that since the length and material of the string is the same, the mass per unit length of the strings should be equal. Alright, so by changing the tension of the string, we are changing the physical properties of the medium. And hence the speed of the wave on the string. Because we're changing the speed of the wave on the string, and therefore we can say so first we can quote the formula first. We can say that V is proportional to the square root of tension. So therefore, because the wavelength is fixed, we know the length is the same. So we know because the wavelength is fixed, and we can say that L is the same, a new set of resonant frequencies can be used to produce standing waves. On the string. So we can quote that V equals to F lambda, therefore V is proportional to F. And that's really all you need to say for this question. And to get a merit, it's just a full explanation. So you need to cover that the tension is proportional to the square root of, the velocity is proportional to the square root of tension. So velocity increases, tension increases. A new set of resonant frequencies are produced. Because the wavelength is fixed, the frequency will increase. Well, not necessarily increase, but will change. And therefore, that will cause the fundamental frequencies to change. So that will get you a merit grade. To get an achieved grade, you can just covering one of those points will get you an achieved. Sarah wants to tune the D string to a frequency 147 Hz. She plays a 147 Hz tuning fork, then plucks the D string on the guitar. She notices a pulsating loudness twice every second. When she gradually increases the tension of the string, the pulsating loudness becomes less frequent and then disappears. Explain the phenomenon that causes the pulsating loudness and why increasing the tension of the string makes it disappear. Alright. For this question, the pulsating loudness is caused by beats, So beats are formed when there are roughly two sounds of equal frequencies played at the same time. So there's going to be alternating periods of constructive and destructive interference, and this causes alternating periods of loud and soft sounds. So that will be the pulsating loudness that Sarah hears. So we're going to describe beat frequencies. So beats cause the pulsating loudness that Sarah hears. Beats are formed when two slightly different frequencies are produced at the same time. This causes alternating periods of constructive interference. The constructive interference, I'm just going to abbreviate as CI because it's too much writing. Constructive interference and destructive interference are abbreviated as DI. So alternating periods of constructive interference and destructive interference causing causing alternating periods of loud and soft sounds to be produced. This is the pulsating loudness that Sarah hears. Alright, so now we have to, so that's point number 1, so that will be point 1. And point 2, we need to start talking about how the tension is affecting the beat frequency. So when the tension is increased, sorry, my writing's very messy. So when the tension is increased, the property of the medium changes. Causing the speed of sound in the string, very important, of string, not air. So causing the speed of wave in the string, okay? So very important, okay? Very important you do not say the speed of the air in sound. The speed of the sound stays the same, okay? Causing the speed of the wave in the string to increase. And you can say the V is proportional to the square root of tension. Therefore, as lambda is fixed, the frequency will increase. Alright, so V is proportional to F. So because beat frequency is defined as the difference between the frequencies produced because the beat frequency is defined as the difference between the frequencies produced, therefore is the difference, therefore the difference is decreasing as the frequency of D string increases. The F, the frequency of the tuning fork, and the D string decreases as F of the D string. So as the D string frequency is increasing, the B frequency is decreasing. So therefore the frequency of the D string must have been lower than the frequency of the tuning fork initially. It's less than that of the tuning fork initially. Alright, so we know that F beat frequency equals to F1 minus F2. Absolute difference. So therefore, in this case, 2. The reason beat frequency is 2 is because she hears the pulsating loudness twice every second. Frequency is how many times per second? So 2 times per second. Frequency is 2. Okay, and that equals to 145. That's F1. Sorry, not 140. 147. Apologize. 147. Minus F2. So in this case, we see that F2 equals to 145 Hertz. And that's our final answer for this question. If you can get up to all the full explanation, you'll get a excellent. To get a merit grade, you need 2 bullet points. So like I said, this is bullet point 1 is talking about how beats are formed. And point number 2 is talking about the tension and how it's affecting the beat frequency. So both of these points will get a merit, and just one of these points will get you an achieved. Question 2, open pipe harmonics. Sam and Miracle are experimenting with a 0.446 meter length of plastic pipe that is open at both ends. When the wind blows across the top of the pipe, Sam and Miracle hear a sound. They assume the sound is made by the air inside the pipe resonating at the fundamental frequency. Show the frequency of the sound is 379 Hertz. At the fundamental frequency, we know that quote-unquote half a wavelength fits into the pipe. Therefore, lambda equals to 2L. In this case, lambda equals to 0.446 times 2. 0.446 times. equals to 0.892 meters. V equals to F lambda, okay, so therefore 338 divided by 0.892, that's our frequency. Frequency equals to 338. 378.92 hertz, and this rounds up to actually 379 hertz. And this is just an achieve level question. Should be. Let me double check. Yeah, just an achieve level. Sam places his hand over the end of the pipe, and the frequency of the sound coming off the pipe changes. Describe and explain the changes in the frequency of the pipe. When it's open at both sides, we know an open end will act like the free end. So on a free end, the wave will reflect on the free end and will undergo no phase change, and it will interfere constructively with incoming waves, and it will cause an area of maximum disturbance and an antinode. So these will be antinodal points. On a closed end, it's going to act like a fixed point, so there's going to be destructive interference. It's going to act like a node, which is a minimal disturbance, point of minimal disturbance. For the antinodes, we see its maximum disturbance. For the fundamental frequency, only half a wavelength will fit into the length of the pipe. Once again, it's very hard to draw on the iPad, so this might not be perfect, but I'll try my best. So it should look something like this. Alright, so it should look something like this. Okay, so that's the fundamental frequency in the open pipe. For the closed open pipe, we have our maximum and our open end, and our minimum and our closed end, and it's going to look something like this. Ooh, very messy, sorry. Sorry, it's just very, very difficult to draw. Alright, so it should look something like that. Okay, it's not perfect, but for the open-closed pipe, it should look something like this. So 1/4 wavelength will fit into this pipe, and 1/2 wavelength will fit into this pipe. Alright, so as we can see, a 1/4 wavelength will fit into this pipe, so therefore lambda in this case equals to 4L, and lambda here equals to 2L. So because there's a change in the wavelength of the fundamental frequency, therefore the speed of the sound and wave stays the same because it's a property of the medium. Therefore, the fundamental frequency itself will change. So therefore, because the wavelength of the sound in the open-closed pipe is double that of the wavelength of the open pipe, therefore it's going to have only half the fundamental frequency, because F equals to V over lambda, and F is inversely proportional to lambda. Therefore, when lambda is doubled, frequency is halved. So we can say so in the open pipe, there are two antinodes created at the open end, and you can say this is maximum disturbance. Okay, so you can say that 1/2 a wavelength will fit, and put the quotation will fit into the pipe at the fundamental frequency. Alright, okay, you can say in the closed pipe and the closed open pipe. Okay, so in the closed open pipe, there is an antinode created at the open end, and a node created at the closed end. So this is minimal disturbance. You can say at the fundamental frequency, only 1/4 of the wavelength will fit into the pipe. Alright, so only 1/4 of the wavelength will fit into the pipe. So now we can say, assuming that the length stays the same, so assuming the length of both of the pipes are the same, so assuming the L of both pipes are Sorry, my writing's very messy. The same. Therefore, we can say that the open closed pipe has double the wavelength than the open pipe at the fundamental frequency. As lambda is inversely proportional to f, the frequency of the open pipe will be double that of the open closed pipe. And that's all we really need to say for this question. So you just need to mention open pipe, 2 antinodes. At the closed open pipe, there's an antinode and a node. For the open pipe, there's half of the wavelength that fits into the pipe. For the closed open pipe, there's a quarter of the wavelength that fits into the pipe at the fundamental frequency. Wavelength for the closed open pipe is actually double the wavelength of the open pipe, assuming that the lengths of the pipe remain the same. Therefore, as f is inversely proportional to lambda, therefore the frequency will be doubled in the open pipe. And that's all we really need to say, and that's a merit level question. To get an achieved, you're looking at correct diagrams will get you an achieved or correct explanation, okay? So correct for merit, you need the diagrams and the explanation, okay? Question C. Sam removes his hand so the pipe is open again at both sides. A strong gust of wind blows across the top of the pipe and causes a much higher pitched sound to be produced. Miracle uses an app on her phone to determine the frequency of the sound is 1138 Hz. Alright, so draw the new standing wave in the pipe. Alright, so we know that F nu, so F nu equals to 1138 Hz. We know that for each fundamental that we increase, it will cause increase of that fundamental. So for example, the second harmonic will have double the frequency of the first harmonic. The third harmonic will have triple the frequency of the first harmonic, and etc. So fourth harmonic will have 4 times the frequency of the first harmonic. Note that the frequency of the first harmonic, I think it was 379. Okay, so that equals to 379 Hz. Therefore, we can say that the n is equal to 1138 divided by 379. Hopefully it's a good number. It should be a good number. Yeah, it's a good number. So this equals to 3.00. So therefore, this is fundamental 3. Not fundamental 3, what am I saying? Third harmonic. Sorry, guys. Third harmonic. For the third harmonic, okay, like I said, it's the antinodes at the open end, okay, maximum disturbance. Okay, and then we're going to have 3 nodes in between the antinodes, okay? That's because on the edges we have antinodes, and in between we're going to have, because it's the third harmonic, we're going to have 3 nodes in between. So we're going to have evenly spaced or 3 nodes, okay? So this is probably not the best spacing. I'll try it again. So better spacing perhaps. Should look something like this. So therefore, our standing wave should look roughly something. Oh, sorry. Okay, not very good drawing. I apologize. Okay. Alright, so that's what our standing wave should look something like this. Okay, so once again, it's not very good looking drawing. However, in the actual exam, you're going to be splitting your pipe into 3 different segments. Okay, 1 segment for each node, very evenly, so you're going to be using a ruler. But in this case, it's very hard for the iPad, so this is an approximation of what it should look like. And this is actually a merit level question, okay? This is actually a merit level question. And achieved is either correct harmonic or correct drawing. Okay, so achieved is here or here. D. Sam has the idea that if he holds the pipe while riding his bike very fast, he can recreate the same frequency in the pipe that the gust of wind had produced. Holding the pipe, Sam rides away from Miracle at a speed of 12.2 meters per second. Sam hears the pipe resonate at a frequency of 1138 Hz, but Miracle hears a different frequency. Calculate the frequency that Miracle will measure and explain why the 2 frequencies are not the same. Okay, so this is obviously a Doppler effect question, okay? So the change, the observed frequency is equal to the actual frequency times by the ratio of the speed of the wave and the speed of the speed of the source. So in this case, Sam is riding away from Miracle, therefore Miracle is going to hear a decreased frequency, therefore we're going to be using the plus ratio. So therefore, we're going to say that the observed frequency equals to 1138 multiplied by speed of the wave, which is 338 over 338 plus 12.2. That should give us a frequency observed is 1098.36 hertz. And we can round that to, that's 4SF, that's 3SF. We probably round that to 3SF, so 1.1 times 10 to the power of 3 hertz, 3SF. Alright, so in terms of why Miracle would hear a different frequency, it's because of the relative motion of Sam away from Miracle. So as Sam rides away from Miracle, each time he produces a subsequent wave, it's going to be a further distance from the previous wave than had he been stationary. So because it's an increasing distance between the two waves, Miracle is going to observe an increased frequency, increased wavelength, and there a decreased frequency. So another way you can look at it is that the number of waves produced by Sam, the frequency he produces, the waves are the same. So the same number of waves are produced, but since he's riding away from Miracle, the same number of waves is actually concentrated in a larger distance. Therefore, the wavelength must be increasing. The observed wavelength must be increasing, and the observed frequency must be decreasing. You can say due to relative motion of Sam away from Miracle. Due to the relative motion of Sam away from Miracle, subsequent waves So now the frequency of waves produced by Sam is the same. So frequency of waves produced is the same. Hence the same number of waves is concentrated in a same number of waves concentrated in a larger distance. Hence, Miracle observes a larger wavelength. So you can say as speed of the wave stays the same. You can say in air, say medium. So you can say that F is inversely proportional to lambda, therefore observed frequency decreases. And that's really all you need to say for this question, okay? So excellence would be a full answer, correct calculation, correct explanation. For a mirror, you need a correct calculation and a brief explanation. What I mean by a brief explanation is just saying, Sam is hearing a Miracle is hearing a lower frequency because she's observing a large wavelength. That would be an explanation, a brief explanation that will get you a merit. And just achieve will just be correct calculation. So excellence is for everything, okay? That's correct calculation and extensive explanation. Merit is calculation and brief explanation, and achieved is just the calculation. Question 3. Using lasers. Lasers are used extensively in scientific research as they are point sources of monochromatic coherent light. In the lab, interference patterns can be demonstrated by shining a laser through a diffraction grating and observing the pattern on a screen. Describe using physical principles why violet maxima bright spots are closer together than red maxima. So for the violet maxima, they have for the violet maxima, they're going to have a lower wavelength, and because they have a lower wavelength, they're going to interfere constructively and destructively at lower angles, smaller angles, and therefore it's going to be a lower distance between adjacent adjacent maxima. For the red ones, it's going to have a larger wavelength, therefore constructive interference and destructive interference occurs at larger angles, therefore it's going to be a larger distance between the adjacent maxima. So we can link that to the formula, that's n lambda equals to d sine theta, that's our formula. So we can say red light has a higher wavelength meaning that it will interfere constructively and destructively at larger angles. So we can say that lambda is proportional to sine theta and sine theta proportional to xn. Okay, so that's the distance between the adjacent maxima. Therefore, distance between adjacent maxima. Well, not increase, will be greater. For violet light, the wavelength is lower. Therefore, CI and constructive interference and destructive interference occurs at lower angles. Therefore, distance between adjacent antinodes or maxima will be smaller. And that's really all you need to say for this question, okay? So comparing the red light and the violet light, okay? So for this question, so basically you can say that correct answer will just get you an achieved. Effective comparison between red light and violet light will get you an achieved. The diffraction grating has 400 slits per millimeter, and the angle between the center and second order maximum is 7. Oh, it's okay. Let me start again. The diffraction grating has 400 slits per millimeter, and the angle between the center and the second order maxima is 20.7 degrees for the violet laser. Show that the slit separation of the diffraction grating is 2.5 times 10 to the power of negative 6 meters. So, simple question here. Okay, we know that there's 400 slits per millimeter. Therefore, each millimeter has 400 slits. Therefore, there will be 400 times 10 to the power of 3 slits per meter. Because 1 millimeter equals to 1 times 10 to the power of negative, equals to 1 millimeter equals to 1 times 1 times 10 to the power of negative 3 meters, okay? So therefore, we know that d equals to 1 over n, so therefore d equals to 1 over 400 times 10 to the power of 3, and that should give us 2.5 times 10 to the power of negative 6 meters. Number 2, calculate the wavelength of laser light. Alright, so in this case, we're going to use our classic formula, n lambda equals to d sine theta. And for these ones, I suggest you draw a quick sketch of a diagram. So in this case, it will look like this. So this is our central maxima. This is our screen. So we're going to have our number one antinode, and we're going to have our second antinode. So in this case, saying that between the angle between the center and the second order maximum is 20.7 degrees. So it's saying that this angle theta, this theta equals to 20.7 degrees. So therefore, in this case, because it's between the second order maximum, our n value equals to 2, okay? So be very careful. So in this case, 2 times of our wavelength equals to d, which is 2.5 times 10 to the power of negative 6, sine of 20.7. So we should find that our wavelength equals to 4.4 times 10 to the power of negative 7 meters. And that should be our final answer. And this should be a merit level question. Okay, if you can get both calculations correct, it's a merit. 1 calculation for achieved. Alright, so question C. Explain the role of diffraction and interference in producing interference patterns seen when light passes through a diffraction grating. So this question is actually, you just need to talk about how when the lights diffract, they'll bend through they'll cause the bending of light through the slits. Therefore, there's going to be many point sources. Okay, many point sources means it's going to be many areas of constructive and destructive interference. Destructive interference occurs when the path difference is a fractional. It's like not a whole number of lambda. Okay, and constructive interference occurs when the path difference is n lambda, a whole number. And at destructive interference, the waves will cancel out to produce a dark fringe. And at the constructive interference, the waves will interfere constructively in order to form a brighter fringe. Alright, so for this one, you can just say light bends through the slits on the diffraction grating to form many point sources. There will be many points of CI. I'm going to abbreviation, so constructive interference, destructive interference. So you can say at constructive interference, the path difference is n lambda, so that's whole number, so n is whole number. And this is when CI occurs to produce a bright fringe on an antinodal line. For DI, the path difference is not a whole wavelength. Hence, there is destructive interference. The waves cancel out to form a dark fringe. You can say, because there are many areas where so there are many point sources for the diffraction grating because there's many slits. So there's many slits, many areas of diffraction, and therefore many areas of constructive and destructive interference because there's more places where the waves will interfere with each other. So many point sources. There will be sharper fringes on antinodal lines and darker lines on nodal lines. And that's because at the antinodal lines, there'll be more areas of constructive interference, therefore it's going to interfere constructively to produce a brighter fringe. For the nodal lines, it's actually going to be more areas of destructive interference, so more chances it's going to cancel out completely to form a very dark fringe. If it was just a 2-point interference source, then there's going to be less areas of constructive interference and destructive interference. Therefore, it's going to be less well-defined sharp fringes, and it's going to be on the nodal lines, there could be a very dim light because it's not fully cancelled out. Okay, so that's the difference between the diffraction grating and the 2-point 2-point experiment. Question D, merit grade. Okay, this is a merit grade question for an achieved. You're looking at 1 point. So basically, if you can say path difference, okay, so that's DI is a fractional path difference and CI is a whole path difference, that'll get you an achieved. Or you can say that destructive interference causes dark fringes, constructive interference causes bright fringes, that also get you an achieved, and both of them will get you a merit. The wavelength of light from the green laser is 5.32 times 10 to the power -7 meters. Describe and explain what will be seen at a point 28.6 degrees from the center of the green interference pattern. So in this question, okay, we can say that we can use our classic formula, n lambda equals to d sine theta. So in this case, trying to calculate the order. Okay, so what order is going to be observed at the 28.6 degrees from the center, from the central maxima. So 28.6 degrees from the central maxima. What is the nodal number, order number, and therefore we can see if this is is this a nodal point? Is this an antinodal point? Okay, so we need to find out this n value. So n times of 3.252 times 10 to the power negative 7, that's our wavelength. That equals to 2.5 times 10 to the power negative 6, that's our distance between slits, sine of 28.6. And if we calculate it, we should get n equals to 2.25, okay? And because n is not a whole number, this is going to be an area of destructive interference. So overall, it's going to be a destructive interference zone. You're going to be observing a dark fringe, okay? And that's because it's a destructive interference. So some people might be saying, but this isn't 2.5, so why is it a destructive interference? That's because the 2.5, so that's the half wavelength, that only applies to the 2-point interference source. That only applies when you have 2-point sources. For the diffraction grating, you have many point sources. Okay, so when you have many point sources, these fractional nodal points here, fractional orders, they're going to be giving you a dark destructive interference. It's going to be overall destructive interference. Okay, so you can say that this is not a whole number for nodal number. No, why am I saying? What I keep saying nodal. I'm sorry. It's order. For the order number. Therefore, this is not a point. This is not a point of constructive interference. This is. Okay, so it's a fractional order. This will be an overall destructive interference, meaning that we should be observing a dark fringe, or maybe like very dull fringes, okay? Alright, so in this case, okay, so that's really all you need to say. So you can correct calculation, correct explanation will get you an excellent. So basically for the explanation, you're just saying that there's overall destructive interference because it's not the path difference isn't a whole number. Therefore, destructive interference is going to be a dark fringe. And for the calculation, is just n equals to 2.25. Both of these points, okay, are going to get you an excellence. For a merit, you can get correct calculation, but your explanation might not be very good. So you maybe incorrect, slightly incorrect explanation will get you a merit. For an achieved, you just need to have a correct calculation. Alright, and that's it for the 2019 Level 3 Waves paper for Level 3 Physics. I hope you enjoyed, and I hope to see